Okay. So today I'm going to take a look at binary search and look at it from a very, very interesting angle. So let me, okay. So binary search is one of the most beautiful algorithms ever created. And I know it's very easy for people because the algorithm is very intuitive, right? If you don't know binary search, just follow me, you understand. It's nothing scary. But it's so important and it's used in so many areas, actually. Like it's used in so many cases. Also, don't forget, I told you if you get a question, a coding interview, and they say the input is already sorted, that means you should be thinking well, right? You should be thinking about using a very optimal algorithm because them sorting it tells you they've already done some pre-processing, some extra work for you. So you should do better. So almost always, consider that. So binary search, sorry. So there's a bunch of search algorithms. We actually have linear search, right? Actually, what do I mean by a bunch of search algorithms? We have linear search. And linear search simply means if you have a list of numbers, right? Let's say 2, 4, 5, 6, 7, 8, 1. And want you to find the number 6, right? What you generally do, linear search, they can start from the first element. You check, are you 6? No, are you 6? Are you 6? Are you 6? Till you find it here, right? So for linear search, we actually end up going through all the elements till we find the number we are looking for. Now, in the worst case, the time complexity is actually O of n. O of n, where n is the number of elements, right? N is the number of elements. That's what we mean by O of n, right? Because we end up processing every single element, right? That is what we call linear search. Now, binary search does something different. Binary search kind of takes your space, right? And then tries to, kind of relatively halve your search space and search a portion of it. That's binary search. But you can't just halve the space if your numbers are randomly distributed. They have to obey some invariant. That is, they must be sorted, right? So that's binary search. It works on sorted collection of objects, on a sorted collection of objects. The sorting order is relatively flexible, but just know there has to be some kind of sort order on your search space. So for instance, if I want to search through, let's say, 1, 2, 3, 4, 5, 6, and 7. Now, the algorithm is pretty straightforward, but the implementation is a bit tricky sometimes for many people. So you're going to stick with, one default implementation, which you can use almost always. You just have to tweak it just a little bit. You see, when we get to the implementation, you realize why I said it's a bit tricky sometimes. So how it works is this. First of all, you say want to divide it, so you find the midpoint. So 1, 2, 3, 4, 5, 6, 7. So our midpoint is somewhere the number 4, right? The number 4. Then, so our mid is simply the length of our list, the length of nums, let's call it nums, right? Divided by 2. So we get this outright. So let's say we get this. Let's say the mid is here. Then we want to divide it into 2 parts. So we're going to have our left here. Please follow the algorithm I'm doing. That's how we're literally going to write the code. Our right here, I'm going to point our mid to this guy here. That's how we're going to do it. Now, if you look carefully, you see where I put the right. Please put the right on the last element. It's going to save you a lot when writing the code. Put the left on the last element and put the mid also on element. Make sure your pointers are actually on element, right? Then you just check. So mid is kind of going to be like kind of your checker. You check is what mid pointing on equal to. So usually searching for some number. Let's call it target or some item. Let's call it target. Okay, let's say our target is set, right? So once we do this, then we check it's 4, right? It's what mid pointing to the target you're looking for. Here, 4 is not 6, right? So then we make a decision. Should we go search here or should we go search here? Right? Now you realize that if we go search this side, if we go search this side, that means we have literally, skipped half of the work. Unlike linear search, where we have to go through the whole thing. Right? Linear search, we have to go through every single thing and process it. But binary search, during every iteration, we discard like half of it, like half of our search space. So here we know that 4 is bigger than 6. Therefore, we jump and then consider just this part. And look at something. We consider just this part. We don't even consider the 4 again, right? Because we already processed it. So we literally, ignore all this part. And now our question, we're dividing and conquering. So this is now what we have here. And here we do the same thing again. We find our mid here, our left is here, and our right is here. Then, luckily for us, our mid, which is 6, is equal to our target, right? And then we have that. So that's how the binary search algorithm works. Literally this. Now let's go to the code. You come across many implementations of binary search, but which can be tricky, can be confusing, especially when people put the right pointer. Just do it this way. Always initialize your left to 0, your right to the last element. Make it point to the last element. So length of nums minus 1. The next thing that is tricky, we are not there yet. Let's say your mid is equal to your length of nums. Actually, don't even compute mid. You compute mid in our loop. Then the next thing you do is this thing, this condition here. Wow, please do it left less than or equal to right. It's going to save you a lot. The thing is, you can do left is less than right, but if you do left is less than right, if I remember correctly, you have to initialize the right to length of num, right? Like this. And something that really confuses people. Sometimes people make it, they make right length of nums and they make the condition left is less than or equal to right. It can trick you, can confuse you. What I tell people is this: just make right length of nums minus one, right? Because that's the index of the last element. Let me stamp on the last element and make a condition less than or equal to r. Does that make sense? Does that make sense? But
Yeah.
sometimes, yeah, this simple thing can really trick you, make you spend so much time debugging your code, right? So if you go this way, make right length of nums, make this condition left is less than r, right? See, I tell people, you already understand the algorithm, but some parts of the code, you just have to kind of memorize it in a way, right? Because of course you understand the binary search algorithm. So it's not a fair thing for just this thing to kind of trick you. So just put this in your head. That's what I did. Just put, I'm going to make my right the last element. I'm just going to make this condition less than or equal to. Then once with this condition, now you compute your midpoint. Your midpoint is always going to be, the main way of computing your midpoints actually. You can make it right minus L divided by 2. You can also make it right, the other way did we even do it? They do right plus L divided by 2. And put this on math. I don't know. Actually plus L. Actually, so these are the two ways of doing it. So you can either, I think the most general one people do is left plus right divided by 2. But this can lead to overflow, right? But it can lead to overflow, but that's something you probably don't want to. I can just mention an interview, but this can be lead to an overflow to show up. You can actually do left plus right minus L divided by 2. So that is something like, if the left is here, right? The left is here and the right is here, right? The position is going to be, now compute this, right minus L divided by 2 is going to be here. But then the actual index is, this plus this. So actually either way, just put one in your head. People usually use this. They can also do this, right? Okay. Then you just compute if nums of n of your midpoint or of your pivot is equal to your target, then that means hooray, you have found it. Good day, right? You can return nums of your midpoint, right? This is a good case. If that's not a good case, LF, right? LF. Please note, some people write if this, they write if this, and so on and so forth. Note, if I change this from elif to if, that means that, assuming there's not return statement here, if it's consecutive ifs, each of them will be checked. But they want to just check one. Like if you check this, you don't want to check this. They have to use if elif. Does that make sense? That is something to also take note of. So elif nums of m, right? So if the middle you are at is big, if it's less than your target, that means you have to come and sit on the bigger 60. That's why it's sorted. So if it's sorted order, we know that if our target is bigger than where we are currently standing at, then we shouldn't even check the smaller elements. We should just go to the bigger elements. How do we go to the bigger elements? We just update our left to be equal to mid plus 1, right? If our current value is not smaller, then it's bigger. So that's our else case. Then we should move our right pointer forward, right? So that is like, you are like 1, 2, 3, 4, 5, right? And you're looking for 2. You're currently at 4. Let's say you're currently at 3, right here. So in that case, you want to move your right pointer from here to here. And then this becomes your new search space. This becomes your new search space, right? So that's the standard algorithm for binary search I would say you should adopt. This is literally it. Get this guy to be 0, right? Standard binary search, make this one length of nums minus 1, and make this the condition. This is general binary search. But here's the thing. Sometimes we apply binary search to other questions. So this is like a very standard one. Find the position of a number and everything, and so on and so forth. Now, I can even tell you find the closest number. It's just this algorithm is twisted. But there are these kind of questions where it is binary search, but it's not clear to use binary search. Let's look at such a question. Please, do you understand this? I want to go to that variance, but I want to understand this first. Does this one make sense? Does this make sense? Does this make sense?
Yep.
Yep. Yeah.
Okay. Now let's go to the next variance, which is very, very crucial. Look at this question carefully. Look at this question carefully. I literally know somebody even got a variance of this question in Microsoft interview just last recruiting cycle. I'm like, yeah, man, this question isn't that bad. Okay, look. So let's assume this. Let's assume that you have you have books to read, right? On a number of days. Let's say you have 10 days to read books, right? And on day one, you can read 20 books. Day two, you can read 15 books. Day three, you can read 12 books. You can read, let's say, 8 books. You can read like 7 books. You can read like 6 books. You can read like, let's say, 10 books here again, all right? These are the number of books you can read, like basically the number of books you can read. And you have a certain, so this is the number of books you can read on any particular day, all right? And then you have a certain restriction. You have a certain variance. Actually, I don't know if I should pull even to put eating bananas. Or should let's just go with this for now. And then now you want to kind of like maximize, the number of days in which you eat. You want to maximize how many books you can eat from a certain slot, right? From a certain slot. So what do I mean by certain slot? So come in. Let me pull. I think I had it typed out here. Give me a second. I want to pull it up so I can share with people and they can read. Uh, sorry, give me a second. Sorry, my thing. Give me a second. I want to pull up the question. I had it typed here. I'm trying to. Okay, if I share my laptop screen, you can see my writing, my iPad. Hmm. Let's see. Maybe we can do it. How do we do this? How do we do this? I can't want to move to my iPad right now. Uh, what do we do? What do we do? Okay, okay. Okay, how about I just write it out here? Okay. So let's say so these are the number of days, right? And you have to read the books, right? You have to read the books. I think it just helps because sometimes people forget the question you're solving. You have to read the books, right? And then you have k number of days, k number of days to read. You have k number of days to read as many books, as many books. Can you see what I'm writing? As you can, right? Now, on a day, right? On a certain day, on each day, you choose a number n, right? So you choose a number n of books which you can read, which you can read. If the number of books left in that day is less than n, you you read all the books. Else, you read n of it, n of it. And the question now is, what is n? Like, choose the best n. This sounds a bit mathematical than I want it to sound, but does the question make sense? So, like, you want to read a number of books, right? Like, you want to read books, and you have, let's say, k days to read all those books, right? Or you can take k to be any. You can take k to be like the limit you have, right? We're like, okay, on every day, right? And we are saying you have to choose a certain number n, where that number n is going to be, is going to be how many books you consume on a particular day, right? And so you can't make n so big, right? Because we want n to be as small as possible, but you still want to maximize the quantity. I want to kind of like find this optimal value of n. I think the best thing to do right now is I should probably share a little question that is similar to this. I think that'll make things clearer. Give me a second. Let me pull this up because I want to explain this question and write code. But doing for my iPad is being a bit challenging. Give me a second. Let me share I think Cocoa Eating Bananas is a good one for this. Okay. Give me a second. Okay, do you pull up boxes here? Can you check the Zoom chat and let's sorry, my Zoom chat is not working even. Uh Give me a second. Sorry, my Zoom chat is okay. Can you check the Zoom chat? I sent a question to the Zoom chat. Can anybody just open that question and read it? That's a similar question. Google eating bananas. Um and just skim that question. I want to use that question to explain this. I will just let me share my screen and let's do it. Give me a second. Okay. Okay. Can you see my screen? So just read this question and I just want to solve this
Yeah.
question. I think it's very important. It lays the foundation for many things. Let's go through it. Please read this question. Try to understand the question. It's a bit convoluted, honestly, but it makes so much sense. Like once you see the solution, like you solve it. Ooh. Do you understand the question?
No.
Please read it. Yeah, I mean, the question's a bit convoluted, but I want people to still read it and get as much as they can. Uh, then after read it together. Has everybody read it themselves? Please read. You just at least read English. Then I'm explaining to look familiar to you. Okay, shall we go through it together now? Okay, shall we go through this? Is everyone done reading for themselves?
Yeah.
Yeah.
Okay, let's read it. Like this, a binary search variant you really need to understand. But there's no concept of sorting here, right? But you're actually going to create a sorted order, right? You're actually going to create a sorted order, kind of in an abstract way, and iterate over it. That's what I want to show you. It's different from the first one we did. So Coco loves to eat bananas, right? And the n piles of bananas. As we said, there are like a number of days, right? And the ith pile has piles I bananas. So like the first, each index has a number of bananas. Like each position has a number of books that you have to consume. Now the guards have gone back and will come back in H hours. So that means Coco has H hours, right, to consume all these bananas, as many as Coco can, right? And it says Coco can decide her banana per eating speed of K, banana per hour eating speed of K. That means that every 1 hour, Coco has to eat a certain number of bananas. We're going to call that K, right? Each hour to choose some bananas and eat K bananas from that pile. Doesn't make sense. So Coco has these bananas that Coco has to eat, and the bananas are in piles. And every hour, Coco can only eat K bananas from a certain pile that they choose. So if you choose pile one, Coco can only eat K from that pile. It can't use that hour to eat from two different piles. That is something Coco cannot do, right? So every hour, she chooses some pile of bananas and eats K from that pile. If the banana has less than if the pile has less than K bananas, she eats all of them and will not eat any more bananas. So even if it's just one pile, and Coco is not eating it, in less than 1 hour, Coco cannot go on to the next on the next pile of bananas. Okay. And Coco likes to eat slowly, but still wants to finish eating all the bananas before the guards return. Return the minimum integer K such that you can eat all the bananas within 8 hours. The most crucial thing about this is one, you want to eat all the bananas, and two, you want the minimum integer K. Because if you don't want a minimum integer, you can be like, okay, every hour, eat, let's say 11. If I take this first example, I'll be like, oh, every hour, like Coco has 8 hours to eat everything. Every hour, Coco can eat 11 bananas. That means that he just needs 4 hours to eat it, right? And 4 is less than 8, so it should be good. But no, 11 is kind of too big. That is, the number of bananas Coco can eat in an hour is too big, right? 11 is too big because 10 will also work, 8 will work, 7 will work, right? I mean, 7 will work. It will also still be less than this. But we want the K to be so small. We want to like restrict this K value so small, right? Like, we want it to be like the minimum K that Coco can still eat everything within 8 hours. Does that make sense? Does the question make sense? Does the question make sense?
Yeah.
Yeah. Yeah.
Yeah, does the question really make sense? Like, it's a bit convoluted, but I want you to kind of make it like practical to you, right? Oh, I should slow down a bit. Okay, let me slow down. Okay, let me go over the question again. So Okay, so Coco goes there and there are bananas, right? Think of bananas as in buckets, right? So there's one bucket, there's one bucket, there's one bucket. Now the first bucket has 3 bananas in it. The next bucket has 6 bananas in it. The next bucket has 7 bananas. The next bucket also have 11 bananas, right? Does that make sense? That's the first line. These are buckets of bananas. Then Coco has 8 hours to eat all these bananas, right? 8 hours to eat all bananas. And you're like, for every hour, in any hour, Coco has to eat a certain number of bananas from any bucket he chooses from. That means that in hour one, if the number Coco has chosen is 3, Coco can eat only 3 bananas from any pile. So if Coco chooses this first pile, Coco can only eat 3 bananas. Yeah, he can eat 3 bananas. Then the next hour, that is hour number 2, Coco goes to this pile and can only eat 3 bananas here. So that means this reduces to 3. So let me actually simulate it here. So we have this. So like so, we have this. Let me just check it out. So we have 3, 6, 7, and 11. So assume that Coco is like, okay, I want my n. Let's make it k. Coco says I want my k to be 3. That means that, and Coco has a maximum of 8 hours. So let's say we have our 1, we have our 2, we have our 3, we have our 4, we have our 5, right? Now in our 1, Coco can only choose 1 pile, and Coco will eat only 3 from it. So let's assume he chooses the first pile at first. So now the piles of bananas look like this. Does it make sense to everyone? Then our 2, Coco chooses the next pile, and he has to eat all the piles. It doesn't matter which pile Coco chooses first, because by all means, Coco has to eat everything. So he eats 3 from here too, right? And then Coco does again, and then Coco chooses, say it's on pile 2, right? Coco is still eating, and then Coco goes to the next one, and then Coco chooses the next pile, right? And then comes here for 11, right? No, Coco has only 8 hours, but we still want Coco to eat everything. Then Coco goes again. That same pile is not done, right? Then you realize it won't be sufficient, right? If you look carefully, you realize that Coco cannot eat. If Coco chooses to eat 3 from every pile, Coco cannot eat everything before the people arrive. Now note, can you see here? Coco has 1 left, right? But even though Coco chose 3, Coco can only eat all the 1 and cannot go on to the next one. Can you see it? Because if you choose a pile of bananas, in that hour, you can only feed on that pile. Does that make sense to everyone? So here, there was only 1 banana left here. Even though Coco's eating capacity is 3, Coco cannot eat 3, right? Coco can only eat that 1, can only consume that 1. Understood? Okay. Then we go to the next one. And then here, Coco can do 0, 0, 0. Then Coco can only do 8 here. Now note, we are on the 8th hour. We're actually on the 8th hour and Coco is not done eating. So that means that 3 was too low, right? 3 was too low for Coco, right? Because see, the time is up. We are on the 8th hour, but who could not finish? There are still 5 left here. Does that make sense? So then you realize that 3 is, potentially binary search is coming in. You choose 3, realize that 3 is smaller, right? So your target is there. Then the midpoint you choose, think of this 3 of 3 now as a midpoint. Now, that could not help you achieve it. So what do you know? What do you do? Do we go to the bigger side or the smaller side? Do we increase K or do we decrease K? What do we do? What do you think we do based on the first algorithm of binary search? What do you think? Should we increase or decrease K?
Increase.
Increase.
We increase K, right? Because if you decrease K, it's going to be worse. People can't eat everything. So yes, we increase K. Now, if we increase K to 4 here, then it can indeed work, right? If you look at this, because if it's 4 here, right? If it's 4 here, it's just going to work. It's just going to work out nicely, right? Then somebody can be like, well, looks like bigger is better. Why don't I just set K to 11? Now, if I set K to 11, you realize that here, day 1, hour 1, Coco can eat everything, right? Hour 2, Coco can eat everything. Hour 3, Coco can eat everything. Hour 4, Coco can eat everything. So it needs to be like just 4 hours, right? But this 11 is an overkill. It's an overkill. Because if I choose 10 too, that will also work, right? If I choose 10, Coco can eat day 1. Coco can eat hour 2. Coco can eat hour 3. Hour 4, there will be 1 left, but hour 5, Coco can eat it. And 5 is still less than 8, right? 9 2 will work, right? So you realize that we can actually decrease it and decrease it. But where can we decrease it to? What is the minimum value we can decrease it to and still have Coco eating all the bananas? Does the question make sense now?
Yes.
Yeah, it does.
Doesn't make sense. Doesn't make sense to everyone.
Yeah, 100%.
Okay, so let's see what we do. So if you look, if you saw, there's kind of like a flavor of binary search in, right? But here, we're not performing our binary search over this value. Performing a binary search over a certain range of values, right? Now, you have to think, what is the range of values? If you look at this, the range of values, what do you think the range of values is? Anyone, what do you think the range of values? What do you think the range of values? In other words, what do you think K can be? Right? What do you think the minimum value of K we should consider? What is the minimum value of K we should consider?
3.
3.
Okay, so 3 is true for this question. 3 is definitely true, but don't just apply to this question. Generally, what is the minimum number of bananas people can eat in an hour? It's 1, right? Because 1 is the minimum value. If you say 0, 0 doesn't work, right? Because if you choose K, K is constant across all, right? So we're going to set our low pointer, that's our left pointer, to 1. Now, what should right be? What do you think is the like kind of the maximum, value we can set K to? The maximum value you can set K to. It can be infinity, right? If I'm like, you can eat 4 million bananas, that is very big, right? But you realize that you can just set it to the max of the number of bananas in any pile. Do you understand? So you can set a right to max of nums, like this. Top right on a chest, right? And this is literally a binary search. We're just going to perform a binary search on this. That is all. To find K. So our target is now K. Does this make sense? Does this first setup make sense?
Yeah.
Yeah.
I hope it makes sense. Okay, let's go to the next thing. The next thing to consider now is we are going to look for, we're going to perform a binary search over a range of numbers. So as I said, your R is actually on a number. So here, it looks kind of sorted, right? So that's like, so the binary search is something like this. Actually, if you look at it carefully, the binary search is something like this. Let me show you. It's like, for this question, it's going to be like left, straight to right. And you have like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This is actually how your binary search is looking like right now. Literally, this is how it looks like. Right? For this question, this is how it looks like right now. And I should have done it for my separation. So then what we do now is, okay, while left is less than or equal to right, what do? We choose the middle value and assume that's our midpoint. I don't know why the planes are flying so low today. Which is our midpoint, right? Our midpoint, as we said, can simply be left plus right divided by 2, right? So let's say we're like, oh, let Coco eat. So here it's like what? 6, right? Or 5. It's 5, right? It's 6, 6. 1 plus 11 is 12. So we're 6. So yeah, our midpoint is here, right? This is what we have our midpoints. We're like, oh, let Coco eat 6, 6 from every pile in every hour and see if that will work out. Now the question is, and see if that will work out. And see if that will work out. That becomes the issue. And see if that will work out. Now let's see how we can see that it will work out. How do we know it will work out? It's work out if we do the simulation we had here. It's work out if we do the simulation we had here. That is, we go through every pile and try to eat, stuff from it, right? We try to eat stuff from it every pile and see if that is going to work out. Does that make sense? Do you understand the concept of see if it will work out? Does that make sense?
Yeah.
Can
Yeah, it does.
you
It
kindly
does.
go over again for that part?
Okay. So we understand how we set this up, right? How we set this up. Do you understand how we set this up?
Yeah.
Okay. And now we're looking for kind of like the optimal value for K, right? We're like, hey, the minimum Coco can eat is 1 banana, right? Every hour. But the maximum Coco can eat is 11 bananas. We want, kind of like the right value, right? Like that sweet spot, right? We're like, okay, let's perform binary search, right? Because as you said, it was kind of like a binary search thing, right? Where you choose a number, you're like, this number is a bit bigger. This number is a bit smaller. And then we're kind of trying to adjust values, right? So now we choose binary search, choose our midpoint to be M, right? And then we choose some value M. So we're choosing M to be 6. They want to check, is 6 sufficient? Is 6 fairly sufficient? Can we use 6? Right? Can Coco choose to eat 6 and still have it work out? Now, if Coco chooses 6 and it works out, then we're like, maybe we can do better. So we try to, because we're trying to minimize, right? We're trying to minimize K. So if 6 works out, what we can do is to try to then, come here and search here. Like 6 works, but can 5 also work? If we come to 5 and 5 works, you're like, okay, 5 also works. Can we still do better? Then we go to 4 and 4 doesn't work. What does that tell us? That means 5 is the minimum value. So 5 is the answer. Does that make sense? It's the same thing as we
Yeah.
did. If we choose 11 and 11 works, we're like, Coco can indeed eat 11. But can we do better? We're like, okay, 10. Then let's try 10. And 10 still works. We're like, oh, okay, 10 works. We're like, okay, can we do better? Then we go 9. right? Then we're like 9 works. Okay, but you see, this is linear search, right? With binary search, right? If 6 works here, we're like, we're not going to do 5. We come to, let's say, 3 because we discard everything here. Does that make sense? So that's kind of like the whole equation. Or if a certain number works, you try to decrease the value and see if that smaller number will work. Like, it's a point where things are broken. Like, oops, the one I saw is probably my biggest one, or stuff like that. That's kind of like a very high level. Yeah, Blake, go for it.
Yeah, so my question is, what if, for
Mhm.
instance, we try 5. So we try 6 and 6 works.
Mhm. Mhm.
Then we try 5 and 5
So if you do
doesn't work.
6,
It means
if you do,
the
it
answer
means 6 is the answer. But 6, yeah,
so
that
we are
is a very
going
high
to
level. But
return
6,
the midpoint minus 1.
not necessarily. So you realize if you do binary, we're going to actually have a value to track, like our answer,
Oh,
right?
okay.
We're going to have a variable here that will keep track of the value we recently saw that worked for us, right? So let's call it result. And at the start, we have no values. Let's set it to -1, right? But you see, in binary search, once we're done processing 6, we actually come to the next middle point, like 3, right? And so on and so forth. But I just want you to, wait, sorry, give me a second. But I just wanted to get, that high level. But if a certain number works, you're like, can I squeeze it a bit more? Can I squeeze it a bit more? You break things. And when you break things, you're like, oops, I couldn't squeeze any further, right? So like, because here, assuming we are done with 6, then we come and try 3. We're like, oops, 3 is less. Look, so 6 worked, right? But 3 didn't work. That means where should you search? You search in here, right? This becomes your new search space, right? Then you check, 4 doesn't work. You're like, oops, 4 is too small. Let's go 5. Then if 5 works, that means 5 is the answer. Does that make sense? But I just want to get that whole equation. Okay, we're a bit beaten by time. Let me pull up. We have to go to the next thing. Let me pull up one of my solutions from recently. That's the only clear one I wrote. Okay, I think we can do this one. Yeah. Let's go through this code. Okay, so here we set it up just like we did, right? So when these are results, right? Then these are pivots, right? And pivot here. By now everybody should be able to write this off here, right? Then we're like, okay, currently, look at this. So currently, okay. So this is the number of hours, right? So if you saw this, sorry, let me do something. How can you even duplicate this? Yeah.
Would the powers be sorted?
No, the files are not sorted. See, that's the cool thing about this. See, how do I get back to what I had at first? Oh, I want to show the simulation I had at first.
I
Can I
think
get back to it?
there's the button at the top corner here, top right corner.
Or
Move your cursor to
top right corner.
the refresh,
Top
the one you
right.
just clicked. No,
Oh,
down.
this one?
Yeah.
But that won't bring the examples I had, right?
Yeah,
You want to
I
go
think
back
it's
to
lost.
Yeah, I wanted
think
to
it's-
show you. I wanted to explain the meaning of this current variable, but you let's go on. So this current variable, right, is going to tell you how many hours you end up using if you choose this k value. Now, if you choose this pivot, right? So like
I
if
think we
when
can
you
make
chose,
it KM.
yeah, what did you say?
Mid-
Yeah, let's make it M because right. So you realize that when we first chose, the target, to be 3, when we're like, oh, let's eat 3 from every power, and when doing that simulation, we're like R1, we're like R1, we're like R2, and R3. How many hours we had to go, to get to everything being eaten? So let's call it, let's say HQ, right? So that's what current is, right? That hey, if you choose this K value to be 3, how many hours will you really need to really finish everything? That is what this current variable is. Does that make sense? Does that make sense to everyone?
Yeah.
Yeah.
Yeah, it does.
Okay. So we've chosen this K value that is, our binary search. Then we go through every pile. Then we try to finish all the pile. That's how you finish all the pile, right? This is like, hey, take all the piles. Look at this. This is nothing tricky. This thing is saying this. Assume you have 12 bananas, right? You have 12 bananas. And your eating rate, you can eat 3. How many hours do you need to finish all 12? How many hours do you need to finish all 12? It's 4, right?
4.
That means that this pile is going to take 12, it's going to take 4 hours. Does that make sense to everyone?
Yeah.
Please, does it make sense to everyone? I just want to tell, like, this is nothing scary, right? That's what this thing is just doing, right? Like this code here. In the same way, if you have 10 bananas and your eating rate It's still 3. How many hours will you need? Because you have to finish everything. How many hours will you need?
3
4.
points.
So
3.
for this, the answer was 4.
And 3, yeah.
So this the answer will be what? It's still 4,
Two.
right?
4.
It's still
Yeah,
4.
4, yeah.
Because if you
Basically,
do 3, you eat 9. One will be left, right? But so here they said that if the pile has less than K, you still have to eat. So here one will be left, but you still need an extra hour to eat that one. Does that make sense? That's why we have the math.seal. That's why we have the math.seal. Because here, if you really divide, the answer is 3.3, right? It's 3.3. But math.sealing, that's why we do the math.sealing. That is the next integer that is closest to, that is higher than this, and that is 4. Does that make sense?
Yeah.
Please, does it make so good? So
yeah,
that's what this thing is.
yes.
So this thing is just saying, if you take the current pile of bananas, that is P, and you divide by the eating rate, the number of hours you need to eat that will be like hours needed. Please follow me carefully. I know it's a bit tricky, but follow me carefully. Hours needed for current pile, right? This is the hours needed for current pile, right? And then after that, I added to, right? That's literally what is going on here. So after I'm done eating all the bananas, since I've gone through every pile, right? Every bucket of banana, I check. Was the total? Don't forget what current is. Current is the number, the hours. Current like here. How many hours you needed to consume everything when you chose, your K value. So if the number of hours I needed was indeed less than H, less than or equal to H, I'm like, then maybe I can do better, right? In other words, if I choose some K value and I'm able to finish it very early, I'm able to finish eating the banana, I ask myself, can I decrease, this my K? Can I decrease my, the value I chose and still do better? That's literally what it's doing here. And this is just binary search. So everything is binary search. The only thing is this part that changes. And this part in the old binary search we wrote is what we had as if nums of pivots equals target. That check here, that check here is literally this part. That is the logic. Here we care about equality, right? And if it's equal, we just return like pivots. But here we wanted to do something better, right? So that's literally the whole thing. So these are binary search templates, and these are kind of questions you come across them quite a lot, where you kind of created, we actually created a sorted order, right? There was a sorted order thing we created, where here the sorted order was over some K values, right? Like we're like 1 up to the max of, some pile, right? This was our sorted order. Then we perform the binary search over this sorted order, right? Does that make sense to everyone?
Yeah.
I know it's a bit some way, but just try to understand it. And
Yeah.
can you use integer division? Integer division won't be the best here. Because if you do integer division, right, 10 divided by 3 is going to be 3, integer division, right? But that's not what you want because they may be fractional values and you want to bump those ones up, right? So please take your time, solve this question and try to understand it. I've come across different questions that use this same this same variation of binary search, where you're trying to find some optimal. So think of it, this is general intuition. Trying to find some optimal value, right? We want to minimize it as much as possible and still have it to work, right? So you divide your range and then you try to do binary search on that range to find that optimal value. There are questions with a flavor like that. Go on this, you can go into these questions and just a couple more. Let's go here. Let's see another one, which you can probably look at. This one is a very standard binary search. So please do this one. This is just vanilla binary search, just implement binary search. Like we already did this, right? We're like
Vanilla binary
yeah,
search.
yeah, just like length is equal to right is equal to this, and you see, just be consistent. I told you. Oh, let me show you the other part. So let's go to how people write their code for binary search. I want to show you something. Let's see most code. So you see, this guy also does the -1, less than or equal to. I want to show you people who don't do the -1. People are very weird in this life. People write it. People write, see, now everybody is getting enlightened. We are all doing the same thing. But you come across, actually, let's just show you here. Let me just show you here. So you see here, we have, let's decrease this -1, and let's make this less than or equal, less than. Right. And then it's beginning to break. It's just beginning to break. Like, it will just it's going to just mess me up and so on and so forth. And then now it works, right? Like, and it will probably fail for some cases too. Oh, this guy is showing messy, right? And it's failed, right? Like, if you don't take it, just do 2 lines and just make your life so miserable. That's why I'm saying, please make this length of this -1 and make this also 2. I want to show you people who actually write it with, but I can't find it. I can't find it. I can't. I can't. It's a recursive approach though, but no one cares about that. Okay, so that's what I had for binary search for today. And please go to the questions or do this one. This great question is very fun actually. It's so pretty. When I saw this algorithm, it's like it's so pretty. There's actually an easier one, there's a medium one, and it's a very cool approach. It's a very, very cool approach. But yeah, but let's go to the other one. You see me, I always make the right pointer kind of the last element, right? It just works for me. Okay, what other one? Try this question too. This question is so tricky. See, this question, I have a friend whom I practice with. Almost always, this question tricks there. It used to trick me too, by the way. That tells you how many times I've tried it. I learn it, then I break it again. I learn it, then I break it again. That tells you my struggles. But yeah, and I had to even draw it out here to just make it seem to work. But try this question. It's so fun, to be honest. Like, teaching with Twitter is so tricky. It's so, but I think if you sketch it, it becomes easier. And it's a question Facebook really likes, this question in particular. I don't have premium yet, so I can't even show you. But yeah, okay, let's go to the next thing. Is this fine? Please go through these questions, and yeah, there's probably more of them. Let's see. There's another question. Oh yeah, let's get it. This one might even be a variation of it. Let's see. Oh look at this question. Can you see? It's actually very similar. Look at this. A conveyor belt has packages that must be shipped from one port to another within days. Just like Coco must eat the banana within 8 hours, right? So days is like kind of your hours. The ice package has a weight of I. Each day we load the package with blah blah blah. We may not slate more than the maximum number of weight. Within the least weight of the ship, that must be on everything being shipped. Can you literally tell it's the same as Coco eating bananas? Can people see it? It's the same thing. Like, it's just a variation. Days is hours. These are your pile of bananas. You know, what should you choose every day? It's the same thing. That's what I'm telling you for like, this thing. That learn these ones for. Like, learn these 150 questions for. Like, master them. Let the algorithm be part of you. If you go to an interview, you get a question like this, because you understood this question, understood the solution, you can easily cook up this algorithm. That is how you do it, right? Like, learn these ones, master them. Okay, let's look at this. Sometimes old age makes you talk a lot. That's the state I'm in right now. Okay. Let's look at someone's solution here. And right, look, it's the same algorithm. This feasible here is literally what we did. Here. That's for loop there with the math with seal and everything. Like, that's just it. He just put it in a helper function here. But is it feasible? Can Coco eat everything? Then blah 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 blah. Don't be like this guy. This guy is one of those who does the less than things and stuff. Let's see if somebody let's see. Came here by accident. I'm not reading this guy's code. Okay, let's just Python. Okay, I guess, well, I mean, probably solution calls for it. Okay, so what's the next one to do today? We're a bit beaten by time. Oh, we are so beaten by time. I wanted to show you another thing. Okay, so did we go through the heaps and the priority queues? I want to just show you one thing. We're almost done. And I wanted to close it early because people have a like, um, this. Okay, I want to show you something. Okay. What question should I even use? Let's take a look at this one. Okay, wait, are folks good to go? Shall we proceed? Oh, we finished right now. Trust me, we finished right now. Are folks good to go? Shall we continue? We're almost done. Ready?
Ready.
Hey, I'm gonna say female. Okay, female. I'm ready, babe. So we all know what heaps are by now. Please, if you don't, go through the materials. I see that's so crucial. I just want to touch on a few things. Now, you know what heaps are used for. If you don't know, please watch the video. Go through the resources. Very, very few resources. Now, when you have a list of numbers like this, right? This is a list, right? You want to create a heap from it, you do heapify. Let's just write heapify here. Please use Python code. Heapify nums. You don't assign it to anything. Heapify does it in place, right? So now when you check nums, it's the heap. It's actually a heap, right? Point one. Point two, that's one of the coolest things I've seen in programming. Heapify is actually linear time, which is really cool, right? Like you're able to construct a heap from a list in linear time. God bless whoever implemented this algorithm. It is linear time. Is that understandable? Is that understood? Now, if you want to, now, whenever you use heapify, Python creates a min heap. Don't know min heap, please don't look at the videos. So point one, you heapify in place. Point two, heapify is linear time. Point three, if you see heapify is a min heap. If you want to create a max heap, what you do is that you have to convert this your num to something like -1, -2, -4, you know, like kind of like just negate every number there, right? Just negate every number there. Look at the trick. After you negate every number there, you know, negative is the same as 0. You negate every number there, you still heapify. Because when you heapify, now you realize that the bigger number ends up becoming the smallest number. Do you all see the trick? When you heapify, kind of like flips things around, right? And so it becomes a max heap. How? Because if you now pop from the heap, if you call it heap pop, you pass the nums to it. If you pop the number, it's going to return to you -4, right? Because -4 is the smallest one. Then you just negate it. So you pop from it, and then you just negate it. And that's your maximum value, -val. Do you all see it? Did this make sense to anyone?
Yeah.
One of my JHS teachers, when he touched chemistry and 1 or 2 people understood it, he thought he had done his job. So let's do that right now. Okay, 2 people understand. Okay, we're good. We're getting there. Yeah. So heapify that is in place. You want to heapify, create a list, then pass it to heapify. Then note this is linear time. Very cool, very cool stuff. This is a min heap, right? It's a min heap. When you create a max heap, what you have to do is negate your element. And when you negate, the bigger number actually ends up being the smallest, right? So if I makes it this, and so on and so forth. And there's the next thing. Sometimes your list is not a straight, you know, list of numbers, right? Sometimes it's something like this. Let's assume you want to. If you go solve this question, the case closest points to the origin, you'd see it. If you look at this question, right now realize that this is our list, right? I call it min heap here. It's going to be a list of lists. It's going to be a list containing numbers, right? Like if I print, let me print it to you. Let's print min heap. Look at how it looks like. Can we all see this? Can we all see this? Now, if you call heapify just like sorting, you see how sorting works. It always sorts based on the first element, right? So here, if you heapify, it's going to heapify it based on the first number in the nested list, right? So you have to sort based on 10. It's to heapify based on 8. Does that make sense? Does that make sense to everyone? The same thing with sorting. If I was sorting this, a sorting algorithm will take the first number and sort it by it, right? So that's something you should keep in mind. Okay, we're done for today. We're a bit waiting by time. Any questions? Any questions?
Yes.
Yeah, go for it.
Yeah, can you touch a bit on the time complexity of the heap algorithms? The heap pop, heap push,
yes,
and
it
all
was
that.
in my head. It was in my head. It was in my head.
Yes, you also said you talk about something today, but I don't remember what you said you talk about.
Yeah, sometimes I
That's
forget a lot of things. Yeah, I'm aging pretty quickly, so sometimes it's just then it's gone. Yeah. So I'll probably remember when we go next week. I remember I said like 3 things I thought about. One was a certain thing, and was this related to financial? I don't know. Maybe listening to my answer. I don't even know. I'll try and think about. I'll try and think again. I'll just time travel. Yeah. Okay. Let's see what I wanted to do here. So right now, hip hop. Very good question. What do you think hip hop is? Anyone guess? If some people already know it. Part-time complexity of hip hop. Anybody?
one.
Also, there's also hip push. Hip push takes the hip and the number you want to push into it. What do you think the time of hip hop is? Pop something from the hip.
Constant time.
Anyone?
Log.
Okay,
Constant
that is
time.
one.
Log.
Okay.
I think
There's a lot of constant time, and
logarithm.
there's now. What is the structure of the heap? What is the structure of the heap? What is the structure of the heap? Now for unkind resources now.
Is it like
It's
a
a
tree?
complete tree.
Like
Yeah,
a
it's a
tree, yeah.
tree.
It's a tree.
It's not just any tree. It's not even just any tree. It's a complete tree. It's a well-balanced tree. It's a beautiful tree, right? Like it's like they built it so well, right?
A wonderful
It's a tree where you cannot even you can even have holes in it, right? And they try to arrange things so nicely, right? Hey, you've probably gone through the resources. I beg, do. I went through it
I
like 2
remember
years
the
ago.
video. I remember the video saying it's a tree with, let's say, if you choose a maximum heap, then the tree will have the parent node, the root node to be
Yeah,
the maximum number in the whole tree, and the children
yeah,
below it has to be either less than or equal to them. And this
or equal
condition
to.
is true for all nodes within the tree.
So that's the last part is a bit tricky. The last part you said. So the condition where the guy bigger, right, is bigger than everything down. It's not necessarily local, but it's not true across the whole tree. It's actually true for like this guy at the top and the guys behind it. But it's possible that under the tree, the condition does not hold, right? It's possible that you can have 4 here and 7 lower, because beneath the roots, everything's kind of loosely arranged for a tree, right? But the guy at the top here, but for the top here, the condition holds. So that's something to keep in mind, right? It's not like self-arranging. Does it make sense?
Okay, so at any instance, maybe like maybe the top 3 nodes are the ones that holds for that condition, for
Yeah,
that
it holds for
invariant.
it holds for this node and every against, so it holds for this node versus this top node versus every other node in the tree, right? So it could be
Okay.
like, but yeah, so that's actually how it holds. But the other crucial thing is there are no holes, right? Like you can't have this guy's left empty and have a node here. There are no holes, right?
Okay.
It's possible to have, please, if we should take that, it's possible to have something like there can be a hole here, right? But there cannot be a hole here. There cannot be a hole here, right? If
Okay,
we
so
look
my
at that,
question is why is it considered a hole if the say for the right subtree, if you have a right node without a left node, it is not a hole. Why?
okay, so there's a concept called is it the last successor node? So the whole I want to pull. Let me show you something. Why do you have a few minutes? People are a bit tired. Let me mention the time complexity and then we consider the holes, right? So time complexity is actually log n, right? Because if you remove this, right, yeah, we try to bubble things up. We have to, do what we call, what's the name? Trickling. That's a word on the material, right? So if you do it, what happens? Okay, this is one reason why we need a hole. Why we don't need a hole. So if you have the 9 here, right? The moment I remove this guy, right? I can push some guy up here, right? I need to fill this slot here. So we know that going up the tree, like the length is kind of like log n, right? Because the tree is very well balanced, right? It's a well balanced tree, and for a well balanced tree, right? Because we don't follow the concept of holes, we actually try to make it balanced. If it's balanced, that means that if there are 8 nodes in the tree, there's going to be 3 levels because it's log to the base 2 of n, right? So removing from the tree is actually log n. If you remove once from the tree, it's log n. If you also add something to the tree, what is it? Okay, I for like people didn't do their research. Please don't look at it again. Thank you. Now look at the cool thing I want to touch on. If you remove once, it's log n. If you're finding the k's largest, you're probably going to remove k times. That makes it k log n. Does that make sense? This is why heap algorithms can be better than sorting. If I'm the kth element and I sort, it's going to be n log n, because sorting sorts everything. Sorting kind of like does a local thing. Like sorting fixes everything, right? Even what you don't need. But a heap is going to prune the tree only k times, right? It's going to heap pop k times. That means that time complexity k log n. Sorting make it n log n. Somebody will be like, well, this sometimes does not matter. That is true. If k is very close to n, then these two are the same. But let's just want the second largest for 1,000 elements. Second largest, that makes it 2 log 1,000. If I do this, I'm going to get 1,000 log 1,000, right? Which is very, very different. It's super different. Even if I do it to base 10, even if I do base 10, this is 8, right? 2 times 3, that is 8. This is 1,000 times 3, 3,000. 8 versus 3,000. That is huge. That's a huge difference, right? So Heaps, if you just want to kill element, Kate largest or Kate smallest, Heap is better than a Sultan. Sultan is just so bad. Does that make sense?
Yes, sir.
Yeah.
But let me show you the other one on the holds. We're a bit behind time, but sorry. Most of you don't even have a live, so let's look at this. Google Drive. Let's take it from our Google Drive.
Why are you saying no? Is it not true?
It's true, but he didn't have to say it like that.
Let's see what we have here. Let's go to our folders. Let's go to our learning materials. Let's go to our textbook chapters. And look, this is a book I read. Almost every time I'm telling you people here, I just read from this book like 2 years ago. Okay. The tree, how do they hold on for complete trees? This tree is not complete. Why? There's a hole here. Can you see the hole here? There's a hole here. Right? That
Yeah.
hole here, because this guy does not have a left node. Let me make it bigger. Let's make this bigger. Okay. Okay. So there's a hole here, right? So this is not a complete tree. But this is complete. There's no hole here, right? And there's no hole here. This is a complete tree, right? So a heap is a tree. That means a heap condition. And it's also called complete. So we have a heap condition here. Let's go to heap condition. Heap
Please,
condition is what? What do you say?
Can I get this book?
Oh, actually, you are right. It's each and every one of his descendants. I feel it's just a local property.
Yeah. So you're saying
I meant this. I meant this actually. I'll still not level by level, right? So you realize that 25 here can be less than the 87 here, right? So how do we communicate this? So across for a specific subtree, the condition holds, right? But across trees. So like this is 25, right? But not necessarily the case that the 25 here should be bigger than everything in the lower level, right? Because you can see 25 here and you can see 87 here. Yeah. I think that's what I meant to communicate. Yeah.
All right. So meaning the way I considered it was, say if you take a how do you call it? If you take a node, you consider it as the parent, then you consider the two children it has. For that node, that the root node has to be the maximum number, and both children has to be either less than or equal to it.
Yeah. For a tree at some node, that condition must hold, and that is actually what helps makes it log n. Because what happens is this: if you want to attach the next element, it comes here, then it will bubble up, bubble here, and bubble here, and come fix it in. Yeah, there is a link to the book. Those of you who don't know this book exists. That's the book I read. And we've been preaching this book till we got tired, so we stopped preaching it. But I'm out from passing time. Yeah, it's a very nice book to be honest. Even I told people like recursion everything. This book really helped me with recursion. Many of the topics I know now, to be honest. I read almost the whole book. But I even had a live though. So imagine I had a life and I still read the book.
Nice.
Yeah. Oh, Jesse has sent the link. Jesse, is that the link to the book?
Yeah, he has.
Okay, good. Okay. So that's it. Have fun. And see, you don't need to read the whole book. Maybe some topic you think, for those of you who are not good at recursion, I would say read this chapter on recursion. Yeah, actually this part, we have a chapter on recursion that is about it was learning to not to write recursive code. It was like even reading recursive code, right? And it was so good. Trust me. This is where I learned assuming the function works from. It was such a new way of thinking, as he has said here.
Your favorite friend.
Yeah, exactly. And it's not a lot of pages. You see, there are code and everything. To be honest, just sit down one day, just read a book. To be honest, you don't need to read every chapter. Just read. See, Heaps is just one chapter, right? So yeah, go through that and it'll be fine. Okay, guys. It was very nice, guys and girls and ladies and gentlemen and other humans. And those who don't know what you are, okay. It was very nice meeting you guys. Let's go on next. Oh, I told about the referrals thing. So we're still wrapping up. I think the message today. Workspace, check if you haven't. We still have a few people we are waiting on to finalize other things. but we definitely hope to, and don't be questioning everything. So long as people be referring you as full timers, so they can refer you September, October, anything like that. That's one of the resume things. Things have been a bit slow for me because my team felt I should get something done. Yeah, and I don't really use my personal laptop now because of my work laptop. But those of you whose messages are in queue, don't worry. I'm using the queue. I'm not doing the stack. Sometimes I do a deck too. But yeah, if you didn't understand, that means you're not learning. Thank you. So I'll catch I'll catch you guys later. Okay, see you guys.
Okay.
Bye.
I see you.